Okay, so we do have a titration curve that's on the review packet that I wanted to go over with you. So the first thing that I always do with my titration curves is I figure out where's the equivalence going to happen. And you can do that using the MAVA MBVB equation. So it's 0.5 molar. We don't know how much acid we'll need, but we know that we have 50 milliliters of 0.1 molar. So this is double concentrated, so it makes sense that we will need 100 milliliters of the thing half as concentrated. Initially, before we start, students are confused about how to write the equation. But before we start, all there is in the beaker is the ammonium and the water. So the initial equation has to have ammonium and water. You know that if it has these two things, or actually no, if it has water as a reactant, you should ice. Okay, you can remember ice, water. And we know water is a reactant here because we haven't added anything yet. It's the initial pH. Okay, at halfway to the equivalence, we get it kind of easy. pH equals pKa. But anywhere in between, we could still figure out what the pH was. And we would do that by saying, say we wanted to figure out after 10 milliliters was added. 10 milliliters is being added to the beaker. So the first reaction that we would have would be NH3 plus H plus, or H3O plus, makes NH4 plus OH minus. Nope, plus H2O. Sorry. Okay, we have H3O plus being added to the NH3. So this tells me that first I would need to Becca. Once I Becca, it's before equivalence, so all of this will go away. We'll only have this and water and NH4 left in the beaker, which tells me that the second reaction would be NH3 plus water makes NH4 plus OH minus. Okay, sorry, I know that's kind of small, but I'm trying to emphasize to you how this is going to work. When the acid is being added, it's a Becca, and because there's not water as a reactant. When it all goes away, water now becomes a reactant, and we can ice. Okay, halfway pH equals pKa. Even though this is a base and we have the Kb, the Ka statement is still true because we could find the pKb, which is equal to the pOH, and subtract, or we could just do it this way. It's more straightforward. This region on the curve is called the buffer region because we have acid and we have conjugate base present. So the second I add one little drip of H3O plus, I have NH3 and I'll have some NH4 left over. Okay, so that is why this is called the buffer region. And once we have equivalence point, we don't have a buffer region anymore because all of the NH3 went away and we only have NH4 plus left over. But we know we did it right because these two things are equal and it's equivalence. And so we have the NH4, divide by the total liters, and ice it out. There's none of these two things left in the beaker, so H2O has to become the reactant. And we remember ice, water. Okay, Becca when there's an acid or a base. And we get a pH of 5.36. And the last one is after. Okay, normally before the equivalence, this all goes away, and then we have a new equation with the NH3 and water. After equivalence, there's some left over. So instead of icing, we can just take the negative log of the H plus. We can neglect anything that the NH4 plus is going to give us because it's weak and we already have a lot of acid just sitting left over in the beaker. Okay, when you graph that on the curve, make sure it looks like a titration curve because it'd be very easy to just put a diagonal line here. You have to add the drop yourself. Okay, because you know what a curve should look like, and make sure you label your milliliters on that axis.